Hey everyone. In this video, I will continue our discussion of hypothesis testing and statistical significance. And as we discussed in the previous videos, whenever we engage in statistical analysis and any type of data analysis, there's one challenge is that we have to kind of distinguish the signal from the noise. We have to be able to evaluate to what extent the patterns that we see in our data are actually, represent some systematic differences in the population, or whether they might be just due to chance, right? And so this kind of statistical framework of hypothesis testing and statistical significance has been developed to ultimately quantify to what extent we can conclude, based on the data that we have, that we can reject some hypothesis about the population. Okay, so let's briefly go over the basic framework. Um, a Most generally, a hypothesis test. What we mean by a hypothesis test is we derive a test statistic based on our data that summarizes the deviation of the data from what would be expected under a given null hypothesis, right? So in our regression framework, this null hypothesis often implies that, for example, a given coefficient would be equal to 0. Okay, we can then compute a test statistic, and based on that test statistic, we can evaluate how likely it is to observe the test statistic that we observed in our data set under the assumption that the null hypothesis was true. And this brings us directly to the p-value. The p-value summarizes the deviation of the data from the null hypothesis. So in other words, the probability of observing something at least as extreme as the observed test statistic. So in other words, we could formulate this as the probability of observing a test statistic. Our ty is the test statistic that we observe in our data that we have, and ty rep is the test statistic over repeated data replications, right? So how likely is it that we observe, given the null hypothesis, assuming that the null hypothesis was true and we had kind of a given sampling distribution under the null, how unusual is the data set that we actually observe and the test statistic that we computed based on that data? Okay, that's basically the whole idea behind hypothesis testing. Statistical significance then is basically conventionally defined as a p-value that is smaller than 0.05. So in other words, we're basically rejecting the null hypothesis if the probability of observing the data, or observing the test statistic more specifically, with our data, if that probability under the null is less than 5%. Okay. Um, so again, kind of to summarize generally, we say that an estimate is statistically significant if the observed value could be reasonably is not statistically significant if the observed value could reasonably be explained by chance under the null hypothesis. Okay, and in this context, and we mentioned this before, it is the possible outcomes of the hypothesis test is either to reject the null hypothesis or to failing to reject the null hypothesis, right? It is never possible to actually accept the null hypothesis. We're always rejecting some kind of a null hypothesis. Okay. So in this framework, in this null hypothesis statistical significance frameworks, there are different types of errors that we can make, right? And the two errors that we discussed in the past are type 1 and type 2 errors, or stated differently, false positive and false negative. Okay, the false positive indicates that we falsely reject a null hypothesis that is in fact true, right? And this is kind of what our significance level refers to. If a coefficient or a test statistic is significant at the 5% level, that means we reject the null. That means we have a 5% 5% chance that we falsely reject the null, because it's possible that that test statistic would have occurred under the null, with a 5% chance. Okay, so that's the false positive, falsely rejecting a null hypothesis that is in fact true. Okay, we can also make the kind of opposite error, which is the false negative. We fail to reject a null hypothesis that is in fact false. Okay, and this is where kind of power calculations ultimately come into play. Okay. The point here, so this is kind of a common framework, not only in political science and social science, but in statistics in general. But the authors of our textbook and a lot of the literature that we're going to read are quite critical of this kind of conventional framework, because it kind of there are kind of issues related to it that I will discuss on the next slide. And they ultimately kind of propose that we should not focus so much on statistical significance, and instead focus kind of go beyond a binary view of something is statistically significant versus something is not statistically significant. Okay. There are a couple of reasons for that, and there are a couple of problems that this kind of binary choice between statistically significant and statistically insignificant brings. One of the problems is that in many applications, in many kind of social science applications, the null hypothesis is kind of like a straw man that is not really realistic. Like, we don't really expect the null hypothesis to be true. Effects aren't really like precisely zero, and so it's a little bit of a question to what extent it makes sense to kind of reject a null hypothesis, especially since the test statistic and significance is ultimately also a function of our sample size. So we ultimately, we can reject any null hypothesis as long as we collect enough data, right? Given that we, can just collect more and more data and then reject any null hypothesis, ultimately the statistical significance doesn't really tell us anything about whether, the effects that we see or the quantities of interest that we observe are actually, scientifically, substantively interesting and important, right? And in addition, after rejecting our null hypothesis, what people, both researchers and practitioners ultimately tend to do is they tend to focus on the point estimates as if those were, measured with precision now that they are statistically significant, right? And that can lead, as I will outline in a second, that can lead to ultimately overestimating the magnitude of effects and underestimating how much uncertainty there is around these effects, right? Because it's not just significant and insignificant. Okay. Gelman and along with co-authors, they in the past proposed alternative kind of perspectives on errors that we can make in the context of significance testing. And these are, rather than type 1 and type 2 errors, these are type S for sign and type M for magnitude errors. The type S error indicates that the sign of the estimated effect is of the opposite direction as the true effect, and the magnitude error is that the magnitude of the estimated effect is much different from the true effect. Okay. And the key point here is that even if a coefficient is statistically significant, so we reject a null hypothesis at p, smaller than 0.05, the probability of having an incorrect sign or the magnitude of the exaggeration of the effect can still be quite substantial, right? So conditional on a coefficient being significant, particularly when we have a lot of variation and a lot of uncertainty, conditional on the effect being significant, there can still be a high probability that the sign of the estimated effect is ultimately in the opposite direction as the true effect, and we're very likely that the magnitude of the effect is actually exaggerated. Okay, so those are important insight that kind of draw attention to kind of issues with like the pure statistical or the pure focus on whether a coefficient is statistically significant or not. Okay. So as I mentioned, the authors of our textbook are quite critical of this conventional hypothesis testing and statistical significance framework. They don't use it in their own work, and we will kind of follow their framework throughout the semester, but we'll kind of take a little bit of a more a broader perspective, since a lot of the research that you read and a lot of the research that is conducted still relies on hypothesis testing and statistical significance. So we will not be as dogmatic as the authors of the textbook in that sense, but rather take a broader view and kind of look at both perspectives. But from their perspective, the problems with the concept of statistical significance are basically multiple. The first one is that, and I kind of alluded at this before, that statistical significance is not the same as practical importance, right? So as we said, just collecting large data sets and large numbers of observations allows you to find significant effects that are essentially substantively meaningless, right? So statistical significance by itself doesn't mean that any coefficient or any effect or quantity of interest is actually substantively important. Another point that is often overlooked is that non-significance does not mean that an effect is zero, right? Insignificance only means that the results are uncertain. We fail to reject the null hypothesis. It doesn't mean that we actually, estimated a precise null by any, by any means, right? Thirdly, this is another point that is often overlooked: the difference between a significant quantity of interest and an insignificant quantity of interest is itself not necessarily statistically significant, right? So changes in statistical significance between one coefficient that is not significant and another coefficient that might be significant, the change between those two coefficients itself is not necessarily statistically significant. And that's another point that is often overlooked when you read a lot of quantitative social science papers carefully. Okay. Another problem that is kind of at the center of the replication crisis in social science research and beyond is the issue of researcher degrees of freedom, p-hacking, and what is called the garden of forking paths. And what we mean by that is that if the only goal is to achieve statistical significance, we also have to recognize that especially in any type of data analysis, there are lots of different choices that can be made in terms of how we analyze the data, how we measure certain key concepts, how we operationalize measures that maybe contain multiple items, and so on. So there are a lot of there's a large number of possible choices that can be made by researchers. So those are degrees of freedom essentially in how to analyze the data. For example, looking at conditional specific types of conditional effects, maybe only looking at specific subsets of the data, and so on, right? And the issue here is that ultimately statistical significance can be attained by multiple potential comparisons, right? And that ultimately makes it possible to ultimately find a statistically significant result from noisy data where there is actually no real signal, right? So that means taking into account all these possible choices that can be made in an analysis, but then only focusing on one specific comparison that happens to be statistically significant, ultimately leads researchers, sometimes even like unknowingly or not intentionally, to strong conclusions that do not really represent the underlying population or the target of the study. Okay, and on top of that, they will fail to reproduce in future controlled studies. So this is ultimately where a lot of the failed replications are coming from, because ultimately, and data sets and studies were analyzed with kind of statistical significance in mind, and as soon as either publication is selecting on statistical significance, or the researcher, the analysis themselves are kind of geared towards statistical significance, then we're ultimately left with results that are less replicable. Okay. Lastly, we have the statistical significance filter, and this is related to this type M or magnitude error that I mentioned previously, which basically states that if we kind of condition on effects being statistically significant in order to be reported in, like, a journal to be published, that ultimately implies that any point estimate that is reported in a journal tends to be an overestimate of the true effect size, because we're selecting on significant effects. Okay, so that's what we mean by the statistical significance filter. So what are we supposed to do, given all these problems with hypothesis testing and statistical significance? What Gell-Mann and his co-authors ultimately suggest is that we have to move beyond hypothesis testing, right? We, rather than having this like binary view of a result is either statistically significant or it's not statistically significant, we have to analyze all our data rather than looking at kind of only a subset. This is kind of related to this issue of the garden of forking paths. We have to take into account all the available data. We have to present all the possible comparisons that we can make, and kind of show variation across these possible different comparisons, and ultimately also make our data public and shared with others, right? So essentially, ultimately what we have to do is we have to kind of acknowledge that there is kind of uncertainty in our results, but we shouldn't think about it as a binary decision between something being significant or insignificant, but rather we kind of should embrace this variation and kind of both understand and communicate how much variation and uncertainty there is around our quantities of interest, without necessarily thinking about one being statistically significant and the other one not being statistically significant. The other kind of conclusion to draw from this is also that we, in some circumstances, we should probably focus on, there might be situations where very small effect sizes we will probably only, we have to recognize that in certain situations with certain studies, we're just not able to detect small effect sizes, right? So focusing on large effect sizes, with sufficiently large data sets, and then communicating your results, that you're kind of fully showing all the analysis, showing all comparisons, and kind of visualizing the uncertainty appropriately is kind of the way forward to go beyond these issues with hypothesis testing. All right, so after this, I will go through another coding example focusing on the coverage probability of confidence intervals.